Hello and welcome to the lectures on state space approach to control system analysis and design. The topic for discussion now is linear observers in this lecture and the subsequent two lectures. So we will start with full order observer first, and thereafter we will discuss the reduced order observer and subsequently the separation principle. So coming to the full order observer, so in the lectures preceding to this lecture, we have done pole placement design of systems in which the aim was to find a control gain K so as to have a desired response of the closed loop system given by a characteristic equation or pole locations. We also did design of state feedback control through the linear quadratic optimal control design, in which the objective was to minimize a quadratic performance index. And one common characteristic between both the design techniques, both the pole placement design as well as the linear quadratic optimal control design, is that in both the cases the control law has the same form given by u equal to minus k times x plus r, where u is the input to the system, k is the state feedback gain, x is state of the system, and r a reference input, as we know. This control law u equal to minus kx plus r can be implemented if the state variables of the system, this x, if they are available for the feedback. Now that was the consideration behind both the pole placement design and the linear quadratic optimal control design. If the state variables are not available for feedback, then what to do? Because that is generally the situation. Some of the state variables may be available, but not every state variable is available for feedback. Rarely it will be a situation that all the n state variables of a nth order system will be available for feedback. Essentially because in many situations there is no existing method or no existing principle for measurement of some of the quantities. So it may happen that even though we intend to measure the state variables, but there may not exist a principle or a method to measure the state variable. Other thing which is mostly the situation is that providing 100% instrumentation is always impractical. Because of various reasons, it could be due to the reasons of cost. So many sensors, I mean combination of transducers and the processing circuits, including the signal conditioning, amplification, etc. So many sensors, obviously they will increase the cost of the overall system. Then there are weight considerations. These transducers need to be mounted, for example, an RTD or a thermocouple, they are to be mounted in thermo wells, and that increases the weight of the system. Then even if the weight can be tolerated, sometimes space may not be available to mount. So in addition, there can be installation issues. So because of the various reasons of the cost, weight, space restrictions, installation, etc., it is most of the time impractical to provide 100% instrumentation in a system. So this rules the scenario. Not every state variable is available for feedback. Only a few of them may be available for feedback. So what is the alternative? So fortunately, if the system is observable, subject to the system being observable, we have seen controllability and observability in one of the preceding lectures. If the system is observable, it gives a guarantee that any initial state can be implemented. And in fact, if the system is observable, it is possible to estimate the unavailable state variables of the system using the available measurements and of course the inputs to the system. And this is done through an observer. The system which does this is called an observer or a state estimator. There is a fine difference between observer and state estimator. We postpone this for a subsequent lecture to understand the difference. Today, let us consider both these terminologies synonymous to each other, observer and state estimator, only for the discussion on observer. So, an estimate of the states of a given physical system can be generated using an observer, and these estimated state variables, the estimated states, can be used to realize the closed loop control law that U equal to minus Kx plus R. So in place of X, we can use the states generated through an observer. That is fortunately possible. Let us see what an observer is. This observer, a definition of observer goes like this. It is a dynamical system, means it will be again characterized by some kind of differential equations. The state variables of the observer are the estimates of the state variables of the dynamical system, the states of which are not available. So a dynamical system whose state variables are estimates of the state variables of another dynamical system is called the observer of the latter system. So basically we have a system U and Y are their respective inputs and outputs. This system description is available. Its states are to be estimated. So we have to make a system which is called an observer. So this is a dynamical system. This is also a dynamical system. This observer is also a dynamical system, and it will generate the estimates of this system. This observer will generate the estimates of this dynamical system. That is the intent. And this it is ought to be a dynamical system. Now it was introduced by Leuenberger in around 60s, and for any observable linear system, an observer can be designed having one property. This is the property. The estimation error, which is defined as the system state X minus the observed state, let me denote it by Z. This estimation error X minus Z can be made to go to 0 as fast as one desires, as fast as it is required. So the Leuenberger observer is a dynamical system which will generate the estimates of the states of a dynamical system, and it will have the property that the estimation error will go to zero very fast. This we will see that the design technique for the observer are very similar to the pole placement design techniques for the feedback system, which we did earlier. We'll see that. Now let us come to how to evolve the equations of the observer. So the dynamic system under consideration is this system given by this state equation and this output equation. X dot is ax plus bu, y is cx. The system input and output matrices are A, B and C. This state X is of dimension n. This input U is of dimension m, and this output Y is of dimension p. So the system is characterized by n state variables, m inputs and p outputs. This is the dynamical system at hand. This is the system given. And for it, the control u equal to minus kx plus r has already been designed. So this reference many times we don't write because in the mathematical treatment it is hardly required. So even when we don't write the full equation, we write u equal to minus kx. The student should understand that always a reference input will be present. So for this system, the linear control u equal to minus kx has already been designed. Now suppose this C matrix was invertible, then it was very easy. Using this equation y equal to cx, one could generate the state x as C inverse y. This is one possibility. However, in this case, this number of outputs has to be equal to the number of states. Then this can be done. But we saw that there are limitations in providing 100% instrumentation. Another possibility is given through the observability Gramian. We have seen in the definition of observer, you may recall, that if the system is observable, then any initial state can be estimated from the knowledge of the system output and the input over a period of time, finite period of time, t0 to tf. And this is the way one determines the initial condition. So any arbitrary initial condition x t0 at any arbitrary time t0 can be determined using this relationship. This we saw while discussing the observability. And once we know the initial condition, then we can determine the state at any other time using that initial condition and the knowledge of input subsequent to that time t0. This relationship can be used. Now there are some problems with this and this we have talked. Let us talk about this also. So in these ways there are difficulties. So as we have said that the number of outputs is definitely most of the situations less than the system order, and C is rarely, very rarely invertible. We can safely assume that C is generally not invertible. And in the other method, this matrix integral has to be determined, which is a complex task. Even if that is done, then there will be susceptibility to measurement errors, and any measurement errors, they will propagate to future estimates of the states, and the uncertainties will also propagate, to the future estimates. So these are the problems associated with determining the state of the system through that use of the observability Gramian and one initial condition which was determined. And of course, we are not using the output subsequent to that time TF, even though the outputs are available. One should use the outputs. So that is why one will not like to use the determination of state through that solution of state equation and initial condition determined once using the observability Gramian. One would not like to do. Instead, one would like to use the observer, which overcomes some of those drawbacks which we just now discussed. So the Leuenberger observer goes like this. We assume at the beginning that the ZT, the observer state, is a dynamical system. Observer state comes from this dynamics. Z dot equal to alpha Z plus beta U plus gy. See, we are assuming that this is the observer, which is a dynamical system, and it is getting U, the input which was going to the system, and Y. That is what observability definition said, that knowledge of input and output can be used to determine the initial condition, and that is the consideration in this. So we are thinking of a dynamical system, the observer, given by this dynamical equation, and the inputs to this are U and Y. And this is the equation. So alpha, beta and G, they are to be determined. Let us see how all this goes. So as I had said, that this dynamical system is excited by the plant input, that U, and the plant output, the Y. And it is of course known as the observer. Now, as was said little while back, that the Leuenberger observer has the objective, has the property that the estimation error xt minus zt, which is denoted by et here, will become 0 sooner or later. It can be made to go to 0 as fast as desirable. So we want that et to be acceptably small and preferably 0. So for that, let us differentiate this relation, and we will get E dot equal to x dot minus z dot. And then this x dot t, it was there in the previous, we know that x dot is ax plus bu. We substitute that. And z dot, we assumed z dot equal to alpha z plus beta u plus gy. We assume this. So we substitute in place of z dot this, because it is with minus, each of these terms has become minus. So we get E dot equal to ax plus bu minus alpha z minus beta u minus gz. And this z we substitute like this, because et is xt minus zt, z can be substituted as xt minus et, which is done here. And beta ut is as it is. Yt we know is c times xt, so that is substituted. So we get this as the right hand side, and we do little more manipulation. So what we will get? This AX, this alpha x, and this GCX, we arrange together, they multiply to xt. And this BUT and beta UT we keep together, so we get this. And this alpha ET, this one is brought here. So the dynamics of the error E is given by this, and based on that we can see that in order that ET becomes 0 asymptotically, it should satisfy these three conditions. Let us see how. This, we say that if it becomes this autonomous equation E dot equal to alpha ET, and if alpha has poles in the open left half as plane, then asymptotically ET will go to 0. That is known. So we use that and we say that this should become 0 and this should become 0. Then that will happen. That is what is written here. This term, both should separately become 0, and eigenvalues of alpha, that should have real part negative. Then ET will become 0 asymptotically. That will be satisfied. So obviously these give that in the observer equation beta should be equal to B and alpha should be equal to A minus GC. It comes from here. And in addition, this alpha should have eigenvalues in the open left half as plane. It should satisfy the property of stability. That should happen. So it becomes like this. We started with this equation for the observer, and because alpha is A minus GC, we substitute that A minus GC, and beta is B, we do that substitution, and G is there as it is. Now we do rearrangement. A times ZT is written here, B times UT, and that GCZT, G is taken common, that CZT is here, and YT. So the observer equation becomes Z dot equal to AZ plus BU plus G, and this difference which is called as residual. This is difference between this observer equation is given by this one. So AZ plus BU plus G Y minus CZ, and this difference Y minus CZ, the actual output of the system plant, and the CZ, that output of the observer, that difference is R, and so the equation can be implemented like this. The observer dynamics can be implemented like this, and this is the state equation for the full order observer. The whole system will look like this. This is the state diagram of the system at hand. It receives the input U and its output is Y, and internally it is X dot equal to A times X, this, plus B times U, and that is integrated to get X. So this is the state diagram for the system X dot equal to X plus B. Now its output Y, it is being picked up and being brought to the observer. Internally, that C times Z, which is the generated like C times X, similarly C times Z, it is the output of the based on the observed state. This is C times Z. So difference Y minus Y of the observer, that is the residual R, G times that will be added to B times U, and A times Z to get the Z dot, and Z dot will be integrated to get the Z, which is the observed value of the state. And if we pick up this state X and this Z, if we see X minus Z, these two, which was defined as E in our slides, this X minus Z, which is E, this E will go to 0 asymptotically. That will be ensured in by those observer equations, which is here, implementation of which will be done by this diagram. This is the full order observer. Now this was the equation. Z dot is A minus GC ZT plus BUT plus GYT. This was the form previous to that implementation which we saw. And we have to select G, yet to be determined. And this is the equation. And alpha has to ensure the stability. Stability of alpha has to be ensured. Poles of alpha should be at desired locations in the left half S-plane. So this problem is similar to a pole placement problem. How? Let us look at the transpose of this equation. If we look, alpha transpose will be A transpose minus C transpose G transpose. And when we did pole placement design, what we saw, the closed loop matrix AC was A minus BK, and thereby we obtained the state feedback K. Now let us compare. They are similar. We get the closed loop system alpha transpose through this open loop system A transpose and the input matrix C transpose. So if we consider A transpose, C transpose as the system matrix and input matrix, then we can get the G transpose and then we can get G. So the design of full order observer can be carried out in the same way as the gain state feedback gain which we did through pole placement. Of course, there the condition was that AB should make a controllable pair. Now similarly, A transpose C transpose should make a controllable pair, which is equivalent to saying that AC should make an observable pair. So if AC is observable, G can be designed to obtain a desired alpha or alpha having a desired characteristic polynomial. That can be done. And of course, as I wrote some time back, this pole placement has to be carried out for A transpose C transpose, thereby we will get G transpose and so G. Now this is shown in the tabular form here. In the pole placement problem, the system matrix is A. For the observer problem, the system matrix is A transpose. Input matrix was B, here it will be C transpose. The gain was K, here we will get G transpose. And this can be, for example, by Bass and Gura formula, which we studied while discussing the pole placement for single input systems through available formulae. So this is Bass and Gura formula. One can also use the Ackermann's formula to obtain the full order observer design. And how one applies the Bass and Gura formula? Just a recall. We have to select the coefficients of a characteristic polynomial denoted by this vector D superscripted by O. So DO has to be selected. These coefficients of A transpose, which are also the coefficients of characteristic polynomial of A, coefficients of characteristic polynomial of A transpose, they are A1, A2, etc. This is the observability or rather let me say controllability matrix, considering A transpose as the system matrix and C transpose as the input matrix. So this matrix P has to be evaluated. W has to be set up like this, in which first row contains 1 and thereafter the coefficients a1 to an minus 1, this one. Second row slipped on to the right, so first one becomes 0, second one 1, and then the fewer coefficients from this one, and so on. This way we set up the upper triangular matrix W, and then we can do the substitution here to get the G transpose. That is how we can use Bas and Gura formula. The student can themselves formulate how it will happen in case one wants to apply the Ackermann's formula. Now let us see this example. We consider this system in which system matrix is this, the input matrix is this, and the output matrix is this. And we intend to design a full order observer so as to have the observer poles at -30 and -2. Now if you see the poles of this system, they will be at S plus 6, S plus 1, 1 and 6. This is the Si minus A. And so S square plus 7S plus 6 minus 6. So one will be at 0, other will be at -7. These will be the poles of this system. And the observer poles are chosen as -30 and -2. That is generally what we do. We select the observer poles further to the left of the system poles. And in fact, not only the system poles, the poles of the closed loop system. So the A minus BK, that when we have designed K and we have seen the closed loop system A minus BK, observer poles are to be taken further left to the poles of A minus BK. That is generally what is done for observer design. So we are anyway considering only the open loop system. The closed loop we are not considering. We just want to see how this observer behaves. So we select observer poles at -30 and -2, and we want to design the observer. That is the consideration. So as I just evaluated, the characteristic polynomial of A is S square plus 7S, and for these pole locations the characteristic polynomial of the observer will be this S square plus 30S plus 60, which is essentially the product of S plus 30 into S plus 2. This product is this. So having selected the pole locations, we get the characteristic polynomial of the observer, and then we apply the formula. So we evaluate the P matrix, which is C transpose and A transpose C transpose. It should come this much. We set up the W matrix. This is 1, A1 and 1. And then we have this as PW, the product of this 1 into -1 minus 6 into 1 0. So 1 minus 6 into 7 1. So that will give 1. And then 0 1 into 1 0 will give 0. And 0 1 into 7 1 will give a 1. So that is PW, and PW transpose is this. And then its inverse will be this. One can verify. And D minus A will be, this is D for the observer, this is A, and so D minus A is this. 32 minus 7, 25, 60 minus 0, 60. And so the G will be given by this. PW transpose inverse into this difference D minus A. That is the gain G for the observer. And so alpha can be obtained as A minus GC, which will be this. A and B beta matrices, alpha obtained, beta matrix will be same as B. So this is that. And the observer will be given by this Z dot equal to A minus GC Z plus beta U plus G into Y. G is this. That is the thing. Now, just to see how the observer states they behave. So we consider a situation in which the given system, that system was in the previous slides. Let me go back. This one, this system, we consider the equilibrium of this system as one, first state x1 being 1 and x2 corresponding, so that the derivative is 0 and input is 0. We consider that. So we get this as the equilibrium condition. This x1 will be 1 and x2 will be 6. 1, 6 will give the equilibrium of the system. Now we assume that no input is applied and the system was at that initial condition. So you can verify that it will remain, the states of the system will remain x1 at 1 and x2 at 6. So this is a plot of x1. It is always 1. However, the observer, if we solve this equation with u equal to 0 and y equal to x1, we get this variation. You can see that this asymptotically, the z1 approaches x1. This red curve, this is the z1 and this is the x1. And similarly, the next plot shows z2 and x2. This is z2, this is x2. So x2 is always at equilibrium because we have not applied any input, and z2 approaches that equilibrium. Now you can see that x1 approached, z1 approached x1, z2 approached x2. So E equal to x minus z approaches 0, 0. Because z1 approaches x1, z2 approaches x2 asymptotically. So this is the E at time t tending to infinity that will happen. And in fact, it happens very fast. It is not in that sense a large t, it is a small t, and it is dependent on that eigenvalues of the observer. So its response will be characterized by e power minus 30t and e power minus 2t. So essentially this will become 0 very fast, e power minus 30t. So this response is essentially characterized by e power minus 2t. That is it. So we, as an exercise, you can consider this this third order system, in which A is given like this, B is given like this, and this is the Cx, y equal to Cx. And you can design observer considering these observer poles. One can consider that. And after design, you will obtain G. So then you have to obtain A minus GC, that closed loop system matrix for the observer. Beta will of course be equal to B. So using that, this alpha, this beta and this G, which you will obtain by this, simulate the system. Both the given system for this input and the observer for this input, and the output of this system that comes by solving. Solve for both xt and zt, and then evaluate the difference et. It will be a column vector with 3 entries. And thereafter see that plot et, three graphs, and conclude, does it become 0 asymptotically or not? It should become 0 if G is properly designed. You will get that. Now let us summarize. The Levenberger full order observer is a feedback system because it took the output of the system, input of the system, and its states, for the feedback as written here. It estimates all the states of the system for which it is designed. So it generates Z which corresponds to X. So number of observer states is N, the number of state variables is N. The order of the full order observer is same as the order of the system. And I have put a question mark, but this we will see that it happens that the state feedback control can be implemented using the estimated value of the state variables through the observer. Can be implemented. We will see while discussing the separation theorem. Now there are some other things to notice. This observer was designed so that state estimation error, that was E, which is X minus Z, this approaches zero asymptotically. Now this is a positive statement as well as a negative statement. The positive statement in the sense that one can design the observer so that it becomes asymptotic and zero in a very short time. Negative statement is that in the theoretical sense it will become zero only at t equal to infinity. But we go by the positive aspect of this statement. If the system is observable, then observer poles can be placed arbitrarily in the open left half S-plane. Of course, subject to the restriction that complex poles should occur as a pair of complex conjugate poles. Observer design is similar to the controller design using pole placement. So all the pole placement formulae can be used to obtain the observer design. Although I took the example of a single input system, even for multi-input systems, the multi-input pole placement formula can be used for obtaining the observer design. And of course, it is very necessary to precisely know A, B and C matrices. So with that, we complete this lecture. Thank you very much. See you in our next lecture.